Okay, so we're going to start. Whoops, lost my mic. We're going to start what I think is one of the most interesting parts of chemistry that there is. It helps explain so many properties of things that we see in our everyday life. And that's something called intermolecular forces, where we're going to look at how solids and liquids mostly, but gases too, interact outside of what we've seen, how they form molecules. Now, we looked at intramolecular bonding earlier. In Unit 5, we built lots of molecules and bonded them together. That is called intramolecular forces. Okay, so that's the forces within the molecule where the bonds happen. And it doesn't matter what the state of the matter is. If it's water, those bonds and the lone pairs of electrons are there no matter what. All right. Intermolecular forces are forces between molecules, and that's a little bit different from the ones that are reacting in the molecule. So let me remind you, way back when, we've learned about ionic bonding, where, for example, the sodium loses its electron completely, the chlorine gains an electron completely, and in a solid state, they form sodium chloride that looks like a crystal. We've also looked at covalent bonding, okay, where we share electrons. In that case, the electrons are what we did with those bonds in Unit 5, forming molecules like this. And although we haven't really looked at it, there's another type of bonding called metallic bonding. Now, those bonds inside of the molecule that we're talking about are very strong. Okay, so we didn't look at how to calculate anything on that, but ionic bonds are very strong. They're full charges attracted to each other by the charges, and that energy is relatively high at somewhere between 400 to 4,000 kilojoules per mole. And we've also looked at covalent bonds, and we spent some time on bond energy and bond length and so forth, where the electrons are shared, and those also have a pretty high energy, anywhere from 150 to 1,100, depending on what we're talking about. Now, I want you to remember that when molecules, ionic molecules, are placed into water, these ions are no longer in a crystal structure. Instead, they separate out and they're hydrated by water. These are water molecules. And all around the water molecule, all around the ion, there's water molecules hydrating those ions. Okay, so here's our chlorine, and maybe here's the sodium ion, and etc. Okay, so I just want to remind you that that's going to come into effect soon. We've also looked at how electrons share, how atoms share electrons to form a bond, and you'll remember that there's some specific bond length that's exactly right, and there's also bond strength involved in these. This is the covalent bonds. Strength. What did I do wrong? Anyway. And we remember when we were learning about covalent molecules, we considered covalent, nonpolar covalent, and polar covalent. So nonpolar covalent are typically considered anything between 0 to roughly 0.5 in the delta En. Remember our electronegativity scale, where we would say, for example, if we have a bond between H and C, H, hydrogen, and chlorine. H would have its bond right here, or its electron right here, and Cl have its electron right here. And when they form the bond, the electron is pulled closer to the chlorine from the hydrogen, because chlorine has an electronegativity of 3.0. This one's 2.1. The delta En is about 0.9. Okay, so that would be a polar covalent. Polar covalent. And we said, on a rough scale, that that's roughly 0.5 to about 1.9 on the delta En. And what does electronegativity mean? It means the ability of an atom to pull electrons towards itself. So in this case, the chlorine is more electronegative than the hydrogen, and right here. And so in our molecule, HCl, if this is our molecule, there's a partially negative pole down here where there's more electrons around the chlorine, and a partially positive charge at the hydrogen where there's less electron density. Now this is important because this is one of the ways you're going to use to help determine your intermolecular forces. I know these are intra, but whether a molecule is polar or nonpolar is important in your analysis here. And so here we have this hydrogen chloride again, or hydrochloric acid. In this case, you can see that the net dipole is towards the chlorine as the electron density is pulled towards the chlorine, and the blue represents electron density. Okay, so that's partially negative. And then this little bit of red here indicates that the electron density is lower, so there's less electron density. Okay, more of it is in the bond here. Instead of being an equal amount, it's mostly pulled, that hydrogen's electron is pulled closer to the chlorine, making this bond. Still bonding here, it's just not as much electron density there. Uh-oh. Oh, thank goodness. All right, so let's go back and analyze how we decided whether a molecule was polar or nonpolar. Remember, you can have polar bonds and still have a nonpolar molecule. So, for example, carbon, I think, is 2.5, and I think oxygen is, I think that's a 3.5 on the electronegativity. And so there is a polar bond here, but since both sides are pulling equally, this is nonpolar. Okay, there's no polarity in this, and they also call it a dipole moment. There's no polarity in this molecule. Likewise, we looked at structures like this SiCl4, all right, and that turns out to be a tetrahedral arrangement. It's both molecular and geometry arrangement, and so this, excuse me, and so this molecule is also not polar. It's a nonpolar, and technically we call that nonpolar covalent. Nonpolar covalent. Well, let's look at when things aren't symmetrical and when they are polar. For example, this is a trigonal planar molecule. Remember, those have 120-degree angles, and et cetera, and et cetera. But because this is our carbon, this is the oxygen, and these are chlorines out here on this COCl2 molecule, the electronegativity for all of these outer molecules pulls the carbon electron density away. It turns out, though, that the net dipole is towards the oxygen. All right, so this end of your molecule is more negative than the other parts. That is a polar covalent molecule. Polar covalent. That means it's sharing the electrons to form the bond, but they're not equally shared. Likewise, here's ammonia, NH3, which, remember, has, if you were to draw its Lewis structure, it would look like this with this lone pair of electrons. And almost all structures, almost all structures with lone pairs of electrons are also polar covalent. Okay, so this is also a polar covalent molecule. Now, that's interesting, and we need to know those things, so you're going to have to analyze them. But what we're really going to look at right now is the interaction between the molecules, the intermolecular forces, which usually I'm going to write IMF, intermolecular. That's what happens between the molecules. So I've got a molecule of water and a molecule of water. How do these two molecules work? What happens in the space between them? Things happen in there. So it's just a quick run through. We're going to have to identify the type of intermolecular forces, and we can't do that until we intermolecular forces between the molecules. But before we do any of that, we have to analyze whether it's we have to analyze if it's ionic, polar covalent, or nonpolar covalent. Okay, well, when it's ionic, it's usually pretty easy to see. So most of our time will be spent on deciding about polarity of covalent bonds. And then we can identify how strong the intermolecular forces are relative to each other. So let's first see what happens, what causes this interaction between the molecules. So that's called the van der Waals radius in terms of covalent things. And so we can have a bond between, in this case, you'll see that they have a whole bunch of chlorine Cl2 molecules together. They must have made it really cold so it would be in a solid kind of condition. There's a bond between the chlorines, okay, holding them together, and that has a certain bond length and strength that we've looked at before. Now, there's a thing called the covalent radius, which is 1/2 of the bond length. We don't really care very much about that right now, but that's technically what's there. What we're interested in right now is something called the van der Waals radius. And with the van der Waals radius, we're talking about between the center or the nucleus and just outside of the molecule. This is just outside of the molecule. There's some force out there caused by what we call the van der Waals radius. And that's the distance, this van der Waals radius is the distance between two non-bonded atoms. Two non-bonded atoms. So you'll see this is Cl2, this is Cl2, but they're not bonded. They're just close together. This van der Waals radius is always bigger than this covalent radius. In other words, those forces in that radius extend past the molecule a little bit. And intermolecular forces are always electrostatic interactions. In fact, everything we've looked at so far has been electrostatic interactions, except we were looking at how they bond. Now we're going to look at how they act together. Now, this is a table in your book that explains to you what the type of charge is, or what the type of interaction is, and gives you some kind of approximate strength. Okay? And so we're going to run through all of these different ones, and then we'll think about how their strength works. Okay, so there are interactions called ion-dipole interactions. Ion, a fully charged molecule, for example, like this potassium, and a dipole molecule like this water. Ion-dipole forces. So when this is a fully charged ion, then it makes sense that the negative end of the oxygen, the water molecule, this is the negative end down here, this is my water molecule, it's charged down here, it makes sense that this would get attracted towards that potassium. Okay? That's a really strong attraction because you've got a full charge from some ion, or maybe a full positive 2, or even a full positive 3, or maybe a full negative 3. Whatever, you have a full charge here, and so anything else around that's charged is going to be attracted, even if it's only a little bit attracted. So those are very, very strong ion dipoles. And remember, dipole just means polar. It really just means a polar molecule. Then there are dipole-dipole interactions. Dipole-dipole. So you have two different molecules, or more, obviously, and the interaction is the space between these two molecules. That intermolecular force is relatively strong. The reason is because any molecule that is polar has some kind of charge. So we might go back to our NH3 and maybe H2O. All right, well, let's assume for the moment that NH3 on this end is partially positive and the H2O also partially negative. They're going to orient themselves in such a way that the negative end is interacting with the positive end and vice versa. So those are dipole-dipole forces. This could also just be NH3s, just a solution of only ammonia. All right. All of these are going to have positive and negative ends to the molecules, or portions of the molecules, and that positive and negative charge allows this interaction. So again, we're looking at electrostatic interactions. Okay. I know, I say okay too much. So what happens in a solid and a liquid when we have two polar kind of molecules, dipole-dipole forces? Well, in the solid, you have this nice arrangement where here's a positive end. It's going to be attracted and interacting with the negative end of some molecule. And it's relatively ordered, and we should know that. Most solids are in some kind of order most of the time. And then the liquids, again, they still interact. Here's our partially negative end interacting with the partially positive end, but these are more disordered. So although the charges and the interactions are still the same, they're very strong, they're a little more disordered than they would be if it was in a solid state. So, in terms of strength, dipole-dipole interactions, well, let me do this one. Ion-dipole is stronger than dipole-dipole. Because after all, on an ion-dipole, we have a fully charged thing. And with the dipole-dipole, we have two partially charged molecules. Now, I also want to talk about something called the hydrogen bond. Hydrogen bond. A terrible, terrible name, because it's not really a bond. It's really an intermolecular force. All right, but the hydrogen bond is a type of dipole. Okay, it's a type of dipole, so we've got some kind of polar molecule. But this force is very strong because it does something called hydrogen bond. All right, so in this case, we have some molecule. Who cares what it is? It's got some positive end at the positive charge at the hydrogen, and that hydrogen bond interacts very strongly with the negative end of some other molecule. Okay, so even though we call them bonds, they're not traditional bonds. They're forces, intermolecular forces, and they're very strong. They can be stronger than polar-polar, dipole-dipole. But they only happen with three molecules, three atoms. Not three molecules, but three atoms. All right. So these only happen when you have an OH bond, an NH bond, and an FH bond. Those are the only times that, now in this case we're talking about something that is actually bonded, okay, between the oxygen and the hydrogen, between the nitrogen and the hydrogen, and between the fluorine and the hydrogen. So in this little picture down here, this could be, for example, NH3 right here. It has a partially negative charge at the nitrogen. And let's say this is water, so we'll put a hydrogen down here. This is the OH bond. This is the OH of water, a bond. But this interaction between the nitrogen and the hydrogen, even though they're two different molecules, is very strong. Okay, and that's what we call the hydrogen bond. Likewise, we can have, for example, if we have HF and H2O, this is H2O interacting, if the hydrogen attached to the oxygen molecule will interact with the fluorine, all right, whatever that fluorine is. So hydrogen bonds are very strong, but they are only in three cases. When there's an OH bond, an NH bond, and an FH bond. Why is that? Well, we're back to this electronegativity business. You'll remember, I hope, that everything in period 2 has really high electronegativity compared to the rest of the periodic table. And fluorine has the highest electronegativity. And oxygen and nitrogen also have very high electronegativity. And also, on our trends, remember our trends, so we might begin with lithium as an atom, pretty big compared to fluorine as an atom, because they get smaller as you go across the periodic table. So atoms decrease across the periodic table in size. And so our fluorine is very, very small, and the oxygen is very small, and the nitrogen is very small. So small with high electronegativity. And that's why this hydrogen bond is only really effective for these three atoms. Okay, so that takes care of things that are polar. What about bonds and molecules that are nonpolar stuff? All right, so we're going to have to think about a concept called polarizability. So let's assume that you've got, for example, how about that carbon dioxide? It's drawn like this. Okay, so carbon dioxide. It's nonpolar, covalent. These two can also get attracted by and induce charges. So, for example, what's happening in this molecule? Here's my CO2 molecule. The electrons between these atoms and in these lone pairs of atoms, and even if they were fully covered, doesn't matter, we could do this with neon too, all those electrons are moving around constantly. They don't ever stop. We can't really decide where they are, but we can make some predictions, remember, about where we think they might be. But they move constantly. They're always moving around. The ones in the bonds, they pretty much stay where they are, but they can still be induced. So what happens is, if you get something nearby that's charged, you can induce a charge in this carbon dioxide. So, for example, I might put carbonated water. I might carbonate water. Okay, so I could put water in the mixture. And I'd have a whole bunch of water in here. And all you have to do is open a Coke, and you'll get the same kind of reaction. But at any rate, I've got all these water molecules around. And these water molecules are polar. Okay, so here's a partially positive one, and it's getting close to this carbon dioxide. What happens? If this is partially positive, then this end is going to develop temporarily a partially positive, let me take all this stuff off for a minute. This end, if this is partially positive, right here, then this end of the carbon dioxide is going to briefly form a partially negative side. Okay, so if this is partially positive, then these electrons are going to be attracted towards the hydrogen. Okay, so those produce a temporary dipole moment. All right, now in polarizability, when it's a nonpolar molecule, this is what we're talking about here, nonpolar, you get a temporary dipole moment. Now, if we were talking about a polar molecule, then we would find that this polarizability enhances the dipole moment. What is polarizability? It's where the electrons in the molecules, which are moving constantly, briefly, even just briefly, develop a charge because more electrons are at one end of the molecule for whatever reason than we would expect, then the next thing also develops a charge. Okay, so what about if we have two? Oh no, I'm not ready there. So we call this interaction that I just looked at dipole-induced dipole. So we have a polar molecule interacting with a nonpolar molecule. The polar molecule is dipolar, and because it's close enough to a nonpolar molecule, it induces a charge. All right, so I didn't realize this, but here is, I think, oxygen. Okay, oxygen, O2, a nonpolar molecule. Because they have the same electronegativity, they're going to pull the electrons the same, amount. All right, and so those are nonpolar. But if you get a water or a polar molecule close enough, you get this interaction, okay, between them. And then this is partially negative on the water. We've got partially negative right here. That's going to induce a partially positive charge in the oxygen molecule. Okay, so dipole, induced dipole means you have a polar and a nonpolar molecule interacting. And then there's another one called induced dipole, induced dipole. So in other words, I have two nonpolar molecules. Okay, so let's assume I have CO2 interacting with CO2. Both of them are nonpolar, but for a brief moment, because of polarizability, this one might develop a positive negative charge at this end. And therefore, in reaction to that, this one would develop a partially positive one. And then in the next molecule, because this is partially positive, this side would be partially negative. And so this would develop a partially positive ending. So you see, it's like a domino effect. If one develops a little bit of polarity for whatever reason, because the electrons are moving and that's all, then the rest that are nearby will also develop that charge. And then you'll have these things lined up with each other. Now, these are also called London dispersion forces. Also, you'll see them LDF, London dispersion forces. And I want to make it clear that because electrons move around in every molecule has London dispersion forces. However, those London dispersion forces are really, really weak compared to compared to a dipole and an induced dipole, compared to a dipole-dipole or an ion dipole. So usually you can't really see these forces because unless it's only nonpolar covalent, everything else is so much stronger. So, but there exists in every single possibility. Okay, so induced dipole, caused by polarizability, have very, very weak energies. Okay, approximately 0.05 to 40 kilojoules per mole. Compare that to the ion dipole, which has really high energy, 40 to 600 kilojoules per mole. So in general, ion dipole is the strongest. Dipole is a close second. Hydrogen bonding, very strong case of a dipole-dipole. This is just a special dipole-dipole. Dipole-dipole. I really once could spell. I know I keep defending myself, but it's true. Anyway, hydrogen bonding is just a special case of dipole-dipole, and then you get the induced dipole-dipole or dipole-induced dipole when you're talking about a polar and nonpolar covalent. And then when you only have nonpolar covalent, that's called induced or London dispersion forces. So, when you're going through these and thinking about these strengths, all right, we've already identified these, but it's good to know which is considered in general the strongest to the weakest. Before you decide about the intermolecular forces, you have to decide what kind of polarity you've got, or ions. So you have to analyze for that molecule for whether it's polar or nonpolar. Then you can determine the type of intermolecular forces that you've got involved, and then you can figure out relative to each other what those how strong those intermolecular forces are. Now, intermolecular forces are very important in things like boiling point, melting point, specific heat, other types of physical processes or physical characteristics. So let's figure out how that works. Okay. First of all, let's go back to the ion dipole. Okay. With the ion dipole, we're starting here with cesium. That's in group 1, way down in period 6 or something. And sodium in group 1, like in period 3. Cesium is a huge molecule. It's got lots of a huge atom. It has lots and lots of electron shells, okay? And so it's easy to pull off the the electron there. And the interaction, because this is so big, the interaction with the nearby water molecule is weaker because that big cesium molecule can't get all that close to the water. Sodium is smaller, okay, so it gets a little closer to the water, and therefore the interaction is stronger as you go up the periodic table. It's also stronger when we have magnesium, okay, again, but this time magnesium is in group 2 and I think period 3. It's a little bit smaller than the magnesium ion, and it can get even closer to the water molecule. Okay, so ion dipole forces increase with decreasing size. All right, it gets stronger when there's more stronger with a smaller size. Now I want to look at dispersion forces. Okay, we looked at the strongest a minute ago, the ion dipole. I want to look at dispersion forces, or the induced, whichever you'd like to think of. You should know both. And how those molecules work. Now, in induced, in something like iodine, first of all, well, here, let me say this. We have increasing strength with increasing molar mass. So the more molar mass, the stronger the intermolecular forces. The bigger the molecule, the stronger the intermolecular forces. And we already know this if you think about what we know about the states of our diatomic molecules. We know that at regular pressure and temperature, iodine is a solid. Remember way back when we did the periodic table. And bromine is a liquid. So right away, we know that there are really strong intermolecular forces between iodine, or otherwise, it would be like chlorine, which is a gas, or fluorine, which is a gas. So we already kind of knew this information. Well, now you're going to put this to work, okay? The bigger the molecule, the more the molar mass in nonpolar covalent stuff, the higher or the stronger the intermolecular forces. And we're going to be thinking about this in terms of boiling point for most part. Okay, the more intermolecular force is equal to a higher boiling point. That should make sense. If the molecules are sticking together in whatever phase they are with really strong forces between them, then they don't want to break up into a gas very easily. Okay, so they have a higher boiling point. Another thing to consider, and we're going to start on, I know I keep promising, but we're going to start on organic molecules pretty soon. We're looking at organic molecules right now. And both of these molecules have a condensed formula with 5 carbons and 12 hydrogens. But this one has a lot more intermolecular force. And that's because it's stretched out. It's got lots of areas that we can utilize to have forces between them. While this one is very compact. All right, it has lower intermolecular forces. In terms of a boiling point, this one is higher. Okay, this one's higher than that one. This boiling point is greater than this boiling point because these have lots of intermolecular forces and this has lesser amount of intermolecular forces. Now, I also want to talk about something else involving boiling point. Okay, so this will be our temperature. And I'm going to look at HCl, HBr, and HI, okay, in terms of their boiling point. And so it doesn't really matter what their boiling points are, but HCl is roughly about minus 90. That's its boiling point. And so we put HCl, if we were graphing, we'd put that about right there. This is HCl. Now, based on what we know, what would you predict would happen to hydrogen bromide? or hydrobromic acid. It's bigger, so we would expect the boiling point to increase because there's more intermolecular forces in bigger molecules. Super, and that's exactly what it does. And likewise, HI also has a higher boiling point. So this is following a trend because these keep increasing. This is smaller in terms of molecular mass. So we expect as the molecular mass increases, we'll see higher boiling points. How can we explain HF with a boiling point way up here? Let's see, the boiling point on HF is like 20 degrees Celsius. Why? What happens here that instead of being like down here, we suddenly have this massive high boiling point? Well, that's because of hydrogen bonding. Remember, this is one of those molecules, when it's bonded together, H and F, it has really strong interactions. This will be partially negative on the molecule, okay, and that's going to interact very strongly with the hydrogen on the next molecule. So this hydrogen bonding happens right here. Okay, where this is partially, the molecule has partially positive and partially negative ends, and so it's polar, and it also participates in hydrogen bonding. So we can see the same kind of pattern here. Here's the ones we just did, HCl, HBr, HI, increasing because they're bigger, they have more forces and stronger forces as they get bigger. Hydrogen fluoride is very, very small. Its molar mass is only like roughly 20 grams per mole. But because the hydrogen is bonded to the fluorine, and because of the high electronegativity of fluorine, it has a very high boiling point. Likewise, if we're looking at period 5, where nitrogen is, we have the phosphorus increasing, arsenic and tin. That's not tin, that's antimony, but whatever it is, also increasing. But look how much higher the ammonia is. Again, that's because ammonia with those N, H, all of these hydrogens can participate in hydrogen bonding to the next nitrogen, ammonia. And water, okay, water is really special. Water has a really high boiling point because it's very polar, and those hydrogen bonds are participating in lots of hydrogen bonding. Okay, now you're going to be thinking about intermolecular forces and how those strengths, how things increase in strength. But I want to talk to you about vapor pressure again, because people kind of misunderstand this. So I want to talk to you in terms of intermolecular forces. So we've got this closed system, okay? Well, let's use this one at equilibrium. Closed system where the gases are the gas molecules are evaporating or condensing at the same rate. They vaporize and go back and forth between the liquid and the gas at the same rate. So we're at equilibrium on that. Now the question here is, let's assume for a minute we have carbon dioxide in a liquid, or I guess we can't do that because carbon dioxide doesn't do well in liquid. Let's do H2O, okay, in a liquid state in a closed container. These have high, strong intermolecular forces. Okay, what kind of vapor pressure, in terms of like a lot or not a lot, do you expect to see when you have water in a closed system? What kind of vapor pressure? What's happening here is the liquid water molecules don't escape very easily from the liquid because of all those intermolecular bonds. Well, some do, okay, but we have low vapor pressure with water. Low vapor pressure. I probably should have used this one for that, but anyway, low vapor pressure. High intermolecular forces, low vapor pressure. What if we take something like, let me see, I know, let's use something like, oh, I know. Okay, let's use CO2 and H2O. So something like your Coke. Okay. What kind of intermolecular forces do we have in here? Just between the carbon dioxide and the water. Between the carbon dioxide and the water, we have an induced, we have dipole, induced dipole. Those are, you know, I mean, they're moderate, but they're weaker intermolecular forces. So compared to the water, these are weak intermolecular forces. What does that mean about the vapor pressure? That means there's high vapor pressure. And so just think about the Coke. When you open the Coke up, the vapor pressure, or the vapors, or the carbon dioxide that have been building up on the inside of the Coke bottle, there's lots of them right up there at the very top, and you can hear them escape. And if it's really hot, or if you're shaking your Coke up, then it's going to explode out. Okay, but that's because these have weaker intermolecular forces, that it has a really high pressure of gas over the liquid. Okay, now intermolecular forces are additive. Okay, they may not be very strong all by themselves, but there's often many kinds of intermolecular forces. So you might have, you will always have some kind of London dispersion forces. Remember, those are always present. You just may not be able to tell them so much, about them so much, because there are other stronger forces. So they can have dipole-dipole. They can have this special dipole kind of force, which is called hydrogen bonding. We could have induced dipole. All of those forces together add up and make things very strong. Okay, so their intermolecular forces are additive. So things like your DNA, a very stable molecule, one that doesn't degrade easily and one that doesn't open up easily. Now there's lots and lots of induced, and that is because a whole lot induced. That is because a whole bunch of your DNA is composed of carbon and hydrogen bonds. And remember, that's nonpolar. That's a nonpolar bond. And then, of course, there's nitrogen. There's nitrogen and hydrogen bonded together. There's carbon and oxygen, very polar. There's a hydrogen bond between this CO group and this NH group. You get this interaction. In fact, the DNA chain has to be broken at the hydrogen bonds to separate it and allow for translation or replication. And unless those bonds are broken, the DNA stays close together in that round, winding, kind of cord-like structure. So that has to be broken, and it can't just be broken willy-nilly. It has to be these have to be broken in just the right way and just the right amount of time. And so these are very, very strong forces. Even though independently they don't mean a lot, add them all together, they get to be very, very strong. And all those forces have lots of influence on everything around you. Okay, how are solids held together? They're held together by intermolecular forces. This desk has lots and lots of intermolecular forces. The gases in this room don't have very many. I mean, unless they run into each other or get close together, they typically aren't going to interact very much. And liquids, somewhere in between, they have relatively strong intermolecular forces compared to gases. And all those intermolecular forces influence all kinds of behavior. For example, we looked some time ago at photosynthesis and the enzymes that pull the solar energy from the sun and give us energy on our planet in so many ways. All of those interactions, or many of the interactions that are involved in that, are because of intermolecular forces. So I personally think this is fascinating stuff. I think it helps put together how so many things work. And so if you're done, basically, when we finish this class with chemistry, at least I hope you can see that there's really interesting forces out there that make the world work, so to speak. And a lot of those are because of the intermolecular forces.